All right, so we're going to take exponentials now, and we're going to do some calculus with them. So we're going to integrate and differentiate them. So this first video is going to be about taking the derivative of exponential functions, and then next we're going to have a video about integrating exponential functions. So the first thing I want you to do is get your calculator out, and I want you to graph the equation y equals x, e to the x. Don't just sit there and wait for me to do it. So when you graph y equals e to the x, you get this, right? And then when you graph its derivative, remember we know how to graph the derivative by putting in like y2, you use the math button, and graph the derivative of e to the x. What you'll notice is the derivative is the exact same, not just like kind of the same, it is the exact same graph. So that's why we use e so much in calculus, because it's so easy. It's just the derivative and the integral of each other. It's always the same. So this is how we differentiate. If you have just e to the x, then the derivative is just e to the x. Okay? If you have e to something else, like some function, we know that we do the peanut M&M, right? The chain rule. So we would do the derivative of the outside function, which would just be e to whatever it still was. And then we would multiply it by the derivative of the inside. Okay? Now, for some of our other exponentials, it's a little bit more complicated, but still not very much. So you take the exponential, it literally stays the same. So if this was 3 to the x, your derivative would be 3 to the x, and we just have to hook on this ln of 3. And then the final option would be, if this was 3 to the 2x, we would have 3 to the 2x times the derivative of the inside function, which is the chain rule, times the ln of 3. So let's see how this actually works in real life, or at least in calculus life. Okay, so we're going to differentiate the first one. We notice that it's e to the x, so we know the derivative of this. Remember that e to the x squared minus 3x is our outside function, and our inside function is x squared minus 3x. So we're going to use the chain rule, and we're just going to say that, so the derivative...
Tyler Adams, could you please come to the high school office? Thank you.
Okay, you're still there. Okay, so the derivative of the outside function is just e to the x squared minus 3x, right? It's the derivative of the outside function, and since the derivative of e to the x is just whatever it is, it stays the same. And then we just have to multiply this by the derivative of the inside function, which is 2x minus 3. Okay? Let's take a look at the next one. This is e to the negative, oh man, I'm just like having trouble getting this. There we go. E to the negative 3 over t. So the derivative of the outside function is the same. It stays the same, e to the negative 3 over t. Then our inside function is negative 3 t to the negative 1. That's negative 3 over t. So the derivative of that is 3 t to the negative 2. So we're going to take the derivative of our outside function, that's our chocolate, and we multiply it by the derivative of the peanut, which is 3t to the negative 2, or you could have written it as 3 over t squared. Okay, now this one, you notice, is not an e. It's going to catch up any second. I just switched it over. There you go. This one is not an e, exponent. So, for this one, remember, we keep the function the same. The derivative is, we keep the function the same. Then we multiply it by the ln of 3, because that's the ln of the base. And then we multiply it by the derivative of the inside function. The inside function is v to the 1/2, and the derivative of that is 1/2 v to the negative 1/2. So then we're going to multiply that by 1/2 v to the negative 1/2, and you're done. That's it. You could like pretty it up a little bit and move it around, but you don't have to. So, please don't let this confuse you. But if you look at our exponential function, our exponential rule, right here, it's really all the same rule. This is the rule, right? If you have any exponential function, you take that exponential function, you repeat it, then you multiply it by the derivative of the inside function, then you multiply it by ln of the base. All of these rules are the same rule. So if you only want to memorize one rule, memorize this one. Because if you think about, so here on e to the x, e to the x, so we repeat the function, then we multiply it by the derivative of the inside function, which is 1, and then we multiply it by ln of the base, which is e. And if you remember from pre-calculus, ln and e are inverse operations of each other, so that is actually 1 as well. So truly, this rule covers literally every exponential that you'll see. It's just sometimes you don't have to do the extra work. You don't have to write ln of e, and you don't have to write times 1, and so on. Okay, so let's look at one more problem where we actually use this as an application, because typically they're not going to ask, maybe in multiple choice or something, but we're not going to ask something like, what's the derivative of e to the 2x, because that's simple. And we like hard in calculus. So a question you might see is something like this: find the relative extrema of this function. Well, the first thing to find relative extrema is we need to find the derivative. And we recognize that this is two functions put together, multiplied together, so we're going to apply the chain rule. So we're just going to define f of x and g of x. I'm going to define f of x as negative x, and that therefore its derivative is negative 1. And then g of x I'm going to define as e to the negative 2x squared. And so its derivative is e to the negative 2x squared times the derivative of the inside, which is negative 4x. So now I have to use the chain rule to find the derivative. So I multiply fig times gif. So I end up with negative e to the negative 2x squared minus, let's see, plus, I'm going to say plus negative x times negative 4x times e to the negative 2x squared. Instead of trying to do all those negatives in my head, I just decided to write them down just in case. So I have negative e to the negative 2x squared, and I recognize those two negatives cancel each other out, and I end up with 4x squared e to the negative 2x squared. So then, that's my derivative. I'm halfway through. That's f prime of x. So, I'm going to go ahead and make that a little bit more apparent. Okay, that's my derivative. Now I have to figure out what's the relative extrema. So remember, relative extrema happen when the derivative is equal to 0. So I'm going to set this derivative equal to 0, and you're going to say, but Mrs. Vardy, I don't know how to do that. I have no idea how to solve this for 0. So remember that when we solve for 0, the first thing we want to try to do is factor, because then we can set each factor equal to 0. And I recognize that both of these have a negative e to the negative 2x squared in common. So I'm just going to factor that out. I'm going to bring my negative e to the negative 2x squared outside, and I'm going to end up with 1 minus 4x squared. And this is still set equal to 0. So now I have two factors, and remember, this function equals 0 either when this function equals 0 or when this function equals 0. So then I look at the e function. Can the e function ever equal 0? No, Mrs. Barney, it can't, because it's an exponential and it has an asymptote. Correct. This one has an asymptote at 0, so it can never equal 0. So the only one that can ever equal 0 is 1 minus 4x squared. So I set that equal to 0. I solve for x. And I have that 1/4 equals x squared, which means that x equals plus or minus 1/2. Okay, so I'm almost there. I now found that I have relative extrema at x equals plus or minus 1/2, and now I have to figure out where to go from there. So remember, our f prime number line. I know, it's been a long time. Did not mean to make that rhyme, but it did. Okay, negative 1/2 and 1/2. So we decide what is going on with f prime when x is equal to negative 1/2 and x is equal to 1/2, or before and after. So if I plug in negative 1/2, not negative 1/2, let's plug in negative 1 into my derivative. Remember, my derivative is negative e to the negative 2x squared times 1 minus 4x squared. Okay, it doesn't matter what I plug into this part of the function, it's always negative, because e to the x is always positive. E to anything is always positive, multiplied by negative 1 is always negative. When this is equal to negative 1, I get 1 minus 4, which is a negative number. So a negative times a negative is a positive. Okay? When I plug in 0, this part becomes positive, and so it's a positive times a negative, which is a negative. And then when I plug in 1, this is positive, the other one is still negative, so now I have, that one's negative and a negative, which makes it a positive. So that means this is an x value for a max, and this is an x value for a min. And then I finally just have to plug those two back into my function to find the points. So remember, my function is negative x e to the negative 2x squared. So f of negative 1/2 is going to be 1/2 e to the negative 2 over 4, so negative 1/2. And then f of 1/2 is just going to be negative 1/2 e to the negative 1/2. Yep, okay. Yes, I'm right. All right, so our final answers is our 2 points of relative extrema are x equals 1/2, y equals negative, or 1/2 e to the negative 1/2, and then when x equals positive 1/2, there's too many 1/2s in here. It equals that. So, there you go. Now on to integrating.